Okay, here we have a quotient or ratio of two functions. So this function has the form u over v, where u is the numerator, which is 5x, v is the denominator, which is x plus 4. Okay, to differentiate this thing we need to get du dx and dv dx. Du dx is 5, dv dx is 1. Alright, so if we call this thing y, so we have y equals u over v, then dy dx, where u and v are functions of x of course, is v times du dx minus u times dv dx, all divided by v squared. Okay, so we multiply v by du dx and we subtract off the product of u and dv dx and we divide the whole lot by v squared. So we're going to get 5x minus 5x here, so those terms cancel, so we just get 20 on top. So eventually we get 20 over x plus 4 squared. Now an alternative way to do this problem is to write 5x over x plus 4 as 5x multiplied by x plus 4 to the power of minus 1, okay? So, you know, this function here is just the same as 5x multiplied by 1 over x plus 4. And x plus 4 means x to the plus 4 to the power of 1. So if we, you know, we can write this thing as x plus 4 to the power of minus 1. Okay, just negate the power. So doing it this way, we can use the product rule combined with the chain rule. So u would be 5x, v would be x plus 4 to the power of minus 1. When we go to work out dv dx, the product rule, we need to apply the chain rule. A curve is defined by these parametric equations. Okay, so we have x as a function of t and we have y as a function of t, and we want to find dy dx. So both x and y are defined in terms of a single parameter t. So to get dy dx from these, we have to get dx dt and dy dt. Okay, so if we differentiate 1, we get 0. If we differentiate e to the minus t, well, if we differentiate e to the power of something, we just get that function back. But by the chain rule, we must differentiate the power with respect to t. If we do that, we get minus 1. Okay, so in general, I'll write it over here. If we differentiate with respect to t, e to the power of a constant times t, where a is any number, in this example it's minus 1, we get a e to the power of a times t. So this comes from the chain rule, which I explained in a previous video. I explained where this comes from. Okay, so that's dx dt, and now we want dy dt. So if we differentiate t squared with respect to t, we get 2t. If we differentiate 2e to the t with respect to t, we just get 2e to the t. If we differentiate e to the t with respect to t, we just get e to the t. And the 2 is just a constant that's multiplied, so we just leave that. That's just multiplied back. Alright, so those are the two derivatives we need to find dy dx. So we get dy dx from multiplying dy dt by dt dx. So dy dt is this here, and that's multiplied by dx dt dx, so we have to invert this thing. Okay, so it turns out that dy dt and dx dt behave like fractions. So that's how we get at dy dx. Alright, so now dividing by e to the minus t is equivalent to multiplying by e to the plus t. So we get minus 2t e to the plus t. And we multiply this term by e to the plus t. So we get minus 2 e to the 2t. Okay, we have e to the t times e to the t. Alright, so just as a reminder, we can write this like this. 1 over e to the minus t is e to the plus t. We could go a bit further and just factorize minus 2 out of this expression here. Next we want the equation of the tangent to the curve at the point x equals 2. Well, we start by getting the slope of the tangent. Well, the slope of a tangent to a curve is the derivative. It's dy dx. But we want to work out this derivative at x equals 2. Now notice that we have the derivative in terms of t. So what we could do is find the value of t that corresponds to x equals 2. So that means that we go back up here. Here we have x in terms of t. If we set x equal to 2, we could solve for t. Okay, so we want to set x equal to 2 and find a value of t that corresponds to that value of x. So finding dy dx at x equals 2 will be equivalent to finding dy dx at the corresponding value of t, which we can easily do by we just plug that value of t into this expression. Okay, so we need to solve this thing here. We get e to the minus t equals 2 minus 1, which is 1. Now this is actually a straightforward equation to solve. E to some number equals 1. Well, that number must be 0. Anything raised to the power of 0 is 1. You can go through the standard procedure for solving it, of course. We want to get at this power, so we take the log of both sides. Preferably the log to the base e or ln of both sides. Ln of 1 you will see is 0. It's the power that we must raise e to get 1. So okay, we get 0 for that. So this is 0. Then we use the laws of logs, which tells us that we can multiply in front by the power. So we stick minus t here, and we get rid of this. Ln of e is just 1. Log to the base e of itself, log to the base e of e is 1. So you see we end up getting that minus t is 0. If minus t is 0, it's obvious then that t must be 0. Okay, so e to the 0 equals 1, so it's quite easy to solve. Right, so that's 0. So dy dx at x equals 2 is equivalent to dy dx at t equals 0. So we just plug 0 into this expression. Well, e to the 0 is 1. We plug 0 in for t there actually. And we have another e to the 0, which is 1. So we end up with minus 2 times 1, which is minus 2. Now, to get the equation of the tangent, we need a point on the tangent, of course. We have the slope of the tangent. So that point will, of course, be the point of contact of the tangent to the curve. We know that point of contact occurs when t is 0. So without knowing what the curve looks like, we can plug 0 in for t into these two equations and figure out the x and y values at that point. So if we plug 0 in here, we get x equals 1 plus 1, which is 2. If we plug 0 in here, we get 0 plus 2 times 1, or 2. So the point of contact is actually 2, 2. Okay, so all I did was plug 0 into the parametric equations. So once we have a particular value of t, we can get the coordinates of a point on the curve. We can build up the coordinates of points on the curve by plugging in values of t. Okay, we can let t range through whatever set of values we want it to range through. But anyway, for this case, t is 0 for the point of contact. So that value of t, particular value of t, gives us that point of contact. Okay. So now we can get the equation of the tangent. So that's just using the equation of a line formula. So here's our point x1, y1. So y minus y1 equals m, which is minus 2, the slope of the tangent, times x minus x1, where x1 is the x value, the point of contact. Okay, and you can simplify that further. But anyway, that's the equation of the tangent. So again, notice that we did everything here without actually knowing what y is as a function of x. We did not know what this looks like. we could, we're able to find the slope of the curve, and the slope of the curve means the slope of the tangent to the curve at any particular point, without knowing how, what the Cartesian form of the function is. Okay, using this diagram here, we are going to write x in terms of sine of y. Okay, so y is the angle. That's straightforward. We can see that in this right angle triangle, x is the side opposite y, and 1 is the length of the hypotenuse. So sine of y is opposite over hypotenuse. Sine of y equals x over 1, which is x. Now we want to show that dy dx is given by this here. Now we can see that y is not given explicitly in terms of x. Here we have an implicit function. Implicit function of y. Well, an implicit function of x. Okay, so y is some function of x, but y is not explicitly given on the left hand side, and something involving x on the right hand side. So to get dy dx, we have to use what's called implicit differentiation. So we differentiate both sides with respect to x. We differentiate the right hand side. Well, the right hand side is just a single term. So I put d dx in front of both sides. So how do we differentiate sine of y with respect to x? Well, we use the chain rule. Okay, so y, remember, means a function of x. Okay, you could write that over here. Y is some function of x. This means equivalent to, just to make it explicit that y is a function of x. That's what I'm doing over here. Okay, so it's like using the chain rule. You just differentiate whatever this function. It's a sine function. The derivative of the sine function is cos. Cos of whatever the argument is. So the argument is some function of x in brackets, say. If we're using the chain rule, this is what we would do. The next step in the chain rule would be to differentiate whatever is inside the brackets. Well, that's y. So we don't know what y is as a function of x, so we just write that down, that we are going to differentiate y with respect to x. Okay. Well, actually we do know what y is. Y is given by inverse sine of x, but we won't use this formulation here. Okay, we're just going to write dy dx. Dy dx is, after all, what we want. On the right hand side we have the derivative of 1x with respect to x. Well, that's just 1, the coefficient of x. So now we can rearrange this to get dy dx. So dy dx is 1 over cos y. But notice now that we can get dy dx in terms of x using this right angle triangle. Okay, that's what we want after all, dy dx in terms of x. The cos of y is adjacent over the hypotenuse. But what is the side adjacent to angle y? Well, we can get that in terms of x because we have two sides of this right angle triangle in terms of x, so we use Pythagoras. So this side here is the square root of the hypotenuse squared, that's 1 squared, which is 1, minus the other short side squared. So we get 1 over root 1 minus x squared. So basically what we've derived here is the derivative of the inverse sine of x. Sine of y is x, so y is inverse sine of x. The derivative of inverse sine of x is 1 over root 1 minus x squared. Now let's look at this function here. We want to prove this equation. You see that we need the derivative dy dx and we need the second derivative. Okay, so this time y is not inverse sine of x, it's actually x plus inverse sine of x. So let's get the first derivative. Well, the derivative of x is 1. The derivative of inverse sine x is just what we showed. 1 over root 1 minus x squared. That's the first derivative. Now we need the second derivative in this expression. So let's get the second derivative. Well, we have to differentiate this thing, so we're going to write it in a more convenient form. So 1 over root 1 minus x squared is 1 over 1 minus x squared to the power of a half. Okay, so the square root of 1 minus x squared means 1 minus x squared to the power of a half. And that's 1 over 1 minus x squared to the power of a half is 1 minus x squared to the power of minus a half. Okay, we just have 1 on top. You could use the quotient rule to differentiate this, but I'm not going to do that. Since we just have a number on top, I'm going to write it like this and use the chain rule. Well, if we use the quotient rule, we'd still have to use the chain rule on this bit here. Then this would be v in the quotient rule. Anyway, we'll just go ahead now and differentiate this. If we differentiate dy dx with respect to x, well, we could write it like this. You know, the notation is d2y dx2 without explaining where this notation comes from. So the derivative of 1 is 0, of course. Now we treat this thing as a single term, like it's x to the power minus a half. And if we differentiate around the brackets, we'd have to get minus a half in front of the brackets times whatever's inside the brackets to the power of minus a half minus 1. That's minus 1 and a half, or minus 3 halves. Okay, we just took 1 from the power. And then we multiply by the derivative of what's inside. Well, the derivative of what's inside is 0 minus 2x, or just minus 2x. You can see the minus 2 and the minus a half cancel each other out. So we get x times this thing here. Well, this is a negative power. I could leave it like that. Okay, so now we are set to write out this expression. So we have 1 minus x squared times d2y dx2, which is this quantity here. We minus x multiplied by the first derivative, which is this thing here. And then we have plus x. And all of this thing is supposed to be 0. Okay, I'll just take this x to the front in this product here. And we've 1 minus x squared to the power of 1 times 1 minus x squared to the power of minus 1 and a half. Well, 1 minus 1 and a half is minus a half. Now I can multiply minus x into both of these terms. Minus x by 1 is minus x, then minus x by this thing here. Well, you can see straight away that the whole thing is going to cancel out. Minus x plus x is 0. This term minus this term is 0. So indeed, this expression here is equal to 0. Okay, here we have to integrate 12e to the power of 3x with respect to x from x equals 0 to x equals 2. So 12 is just a multiplicative constant, you know, it can be just taken out through the integral sign. So what we want to do is find a function whose derivative is e to the power of 3x. So I'll just write down what that is. We would have to have 1/3 e to the 3x. Now you see, if you differentiate this with respect to x, you'll be using the chain rule. So I'll just write it over here. Let's suppose that we are differentiating this with respect to x. 1/3 e to the 3x. Well, the 1/3 is just a multiplicative constant that can be taken out. So we're differentiating e to the 3x with respect to x. Well, if we differentiate e to the power of something, we just get it back. And by the chain rule, we differentiate the power. If we differentiate 3x with respect to x, we get 3. So you see, we do indeed get e to the 3x. So this is the correct answer. This is the integral of e to the 3x with respect to x. So in general, if you're integrating e to the power of a constant times x with respect to x, you get 1 over that constant times e to the constant times x. So a is any constant. So this is the general situation that's worth remembering. Okay, so we get 12 times a third, which is 4, so we get 4 e to the 3x for our answer, and we want to evaluate this from x equals 0 to x equals 2. So we plug in the upper limit, which is 2, so we get 4 e to the 3 times 2, or 4 e to the 6, and then we have a minus sign. Next we write this out, replacing x with the lower limit, which is 0. So that's going to give us 4 e to the power of 0. Well, e to the power of 0 is just 1, so we get 4 times 1, which is 4. And you can see that we can factorize 4 out of this, so we will indeed get it into this form. Some number times e to the power of another number minus 1. So we get 4 e to the 6 minus 1 actually. So as a reminder, the geometrical interpretation of this definite integral is that we got the area between the curve and the x-axis between 0 and 2. So this area here is given by whatever this is. Okay, here we have a cubic function, but a and b are missing. However, we are given that this function has turning points at x equals 2 and x equals minus 4/3. So apparently that is enough information to find out what a and b are. So if there's a turning point at x equals 2, it means that the curve is neither increasing nor decreasing at x equals 2. In other words, the slope of the curve is 0, or the slope of the tangent to the curve at x equals 2 is 0. Now the slope of a curve we know is given by the derivative. So if we differentiate this, we get 3x squared plus 2ax plus b. Okay, a and b are just constants. So that's what we would do if we knew what a and b are. This is what we would do to get the derivative. And at x equals 2, the derivative is 0. The slope of the curve is 0. So the derivative at x equals 2 is given by 3 times 2 squared plus 2a times 3 plus b, and that's 0. That's the key point. There are two unknowns in this, of course. If we simplify this a bit, what do we get? We get 3 4s are 12 plus 6a plus b equals 0. Alright, the derivative at minus 4/3 is also 0. Okay, the slope of the curve at minus 4/3 is 0. So we just plug minus 4/3 in for x. Okay, if you want to, you can simplify this by multiplying it all by 3. So that's going to give us 16 minus 8a plus 3b equals 0. So now we have two equations and two unknowns, and we can solve between them to find a and b. I just made a slip here. F prime of 2 is 2a times 2, so this should be 4a. Anyway, I won't solve between these two linear equations with two unknowns. That's straightforward. You will get a equals minus 1 and b equals minus 8. So now we can write down f of x. F of x is fully specified. So a is minus 1. So we can write just minus x squared here. And b is minus 8. Next we want the coordinates of the turning points. So that's straightforward because we have the x values of the turning points. So we want the y values. So the turning points are points on this curve, of course. So by working out f of 2 and f of minus 4/3, we'll have the y values of both turning points. Alright, so I've worked out f of 2 and f of minus 4/3. So f of 2 is minus 12 and f of minus 4/3 is 176 over 27. Now you can see straight away that this must be the local maximum, because this value is greater than this value here. Okay, so the only way to draw a curve whose turning points are at this point and at this point is to make this one a local maximum, which means that this one down here must be the local minimum. So our cubic function must look like this. Okay, let's look at the graphs of y equals 4x and y equals x cubed. Now y equals 4x is a linear function, so it's a straight line. So we only have to pick 2 points to draw this. So when you can see that when x is 0, y is 0. So 0, 0 is on that line. When x is 1, y is 4. Okay, so those are 2 points on the line, so I'll just draw this in roughly. So we have a straight line, y equals 4x. Also, by comparing it to the form y equals mx plus c, if y equals 4x, then m is 4, the slope of the line is 4, and c is 0, the y-intercept, where the line cuts the y-axis. So if the slope is 4, then, you know, if we pick a point and increase x by 1, then we must go up a distance of 4 to meet the line. Alright, so that's the line. Next we have y equals x cubed. Now this is a cubic function. Normally cubics have 2 turning points, but this particular one doesn't actually have a turning point. Now, if you plug 0 in for x, you get 0 cubed, which is 0. And as x increases, it's pretty obvious that this function will increase. And it actually increases this way, like this. And as x gets large, x cubed gets large very quickly, much more quickly than the case than 4x does. So eventually the curve will cross the line. It'll happen pretty quickly actually. And what about here? Well, if you graph the thing on the other side, you'll actually get the same shape as on the right hand side. Let's see why that's so. Let's take let's say 1. Okay, 1 cubed is 1. What about minus 1? Well, if you work out minus 1 cubed, you get minus 1. Okay, this isn't drawn very well, but so 1 cubed is 1. Okay, I'll write that down. Minus 1 cubed is minus 1. Okay, so you can see what's happening here. We just changed the sign. It's like we're just flipping this thing, we're flipping it over. Okay, if we take another example, suppose we have, I don't know, 2 cubed. 2 cubed is 8, of course. But minus 2 cubed is minus 8. Okay, this thing is called an odd function. Y equals x cubed is called an odd function. Because, well, I'll explain it by just changing the notation here a little bit. Instead of y, I'll write f of x. Let's consider f of minus x. I looked at particular values here, but let's look at the general case. Alright, so x is some general value. F of minus x is minus x cubed. But minus x cubed is that. Minus x all cubed is minus x cubed. So the value of the function at x is x cubed, but the value of the function at minus x. Okay, so we get this kind of symmetry here. Reflect x through the origin. We get minus x cubed, just like we reflect x cubed through the origin. So the graph gets kind of flipped over. So f of minus x is minus x cubed, but minus x cubed is just f of x. So for an odd function, f of the negative value is minus f of, say, the positive value if x is positive. So basically, this part of the graph will have the same shape as this part of the graph here. The line is also an odd function. Okay, if we call our line f of x. Okay, now this is for the line. Okay, y equals 4x. we work out f of minus x, we get 4 times minus x, which is minus 4x. But minus 4x is just minus this thing here, which is minus f of x. So f of minus x is minus f of x. Anyway, this stuff is really just an aside. You know, you can ignore this. It's just to show you that the shape of the curve is the same. Below the x-axis as it is above the x-axis. It's just flipped over. Right, we want the area of the region in the first quadrant enclosed by the two graphs. This region here. So this is the first quadrant. Now, what we do is we get the area under the curve, or the area between the curve and the x-axis in this quadrant, by integrating from 0 to whatever the x value of this point is. So we have to find the x value of this point, and that will give us the area under the curve. Actually, I'll do this in blue. So how do we find this point? So we want to find the value of x for which x cubed is equal to 4x, for which these are equal. So we just put them equal to each other. We set x cubed equal to 4x. Okay, so whatever this value of x is, if we plug it into either this function or the other function, we get the same result. So we set these equal to each other to find the value of x that makes them equal, essentially. Anyway, okay, so we have x cubed minus 4x equals 0, and we can factorize x out of this. Now, product of these factors is 0, so that means either of them must be 0. So x equals 0, well that's this point here, of course, that's obvious. From this here we get x equals the square root of 4, which is plus or minus 2. So graphs intersect at x equals 2. Okay, so this isn't drawn very accurately, but anyway, we want to get the area under the curve from x equals 0 to x equals 2. So that involves integration. By the way, at the other side, by symmetry, this is going to be minus 2. Okay, the coordinates of the x coordinate of this point is minus 2. Alright, so to get this blue region, we integrate from 0 to 2, the curve, which is x cubed with respect to x. If we integrate x cubed, we add 1 to the power to get x to the 4, divide by the new power, plug in the upper limit, so we get a quarter times 2 to the 4. 2 2 is 4, 2 4 is 8, 2 8, 16. 16 divided by 4 is 4. Okay, we get 0 if we plug in the lower limit. Okay, so this area is 4. Next we will get the area under the line. Okay, so that involves integrating from 0 to 2 again, of course. So we're going to get all of this area here. The equation of the line is 4x. So integrate 4x with respect to x. So we add 1 onto the power to get 2. And divide by that new power, so we get 4 halves x squared, which is 2x squared. And plug in the upper limit to get 2 times 2 squared. That's 2 times 4, which is 8. Plug in the lower limit, well that's just going to give us 0. So the answer there is 8. So finally now we can get the area in here. It's just the area between the line and the x-axis, which is 8, minus the area between the curve and the x-axis, which is 4. So that's going to give us 4. Next we want the total area enclosed between the two graphs. Well, we just use symmetry here. So as I explained to you earlier, this part of the graph has the same shape as part in the first quadrant. So this area will be the same by symmetry. So this area is also 4. So the total area is 4 plus 4, which is 8. Now when I say the graphs are symmetric, both parts of the graph have a symmetry, I mean that the graph is symmetrical under central symmetry in the origin. So to look at this another way, we could pick any point on the curve. So the x value is just some general value, which we call x, of course, but then the y value is given by x cubed, the equation of the curve. So this point here has coordinates x, comma, x cubed. Now get the image of this point under symmetry in the origin. So we draw a line from this point to the origin, and we go out the same distance on the other side, of course. So we make these distances the same. So what's the coordinates of this point? Well, we know that when we map a point through the origin, the coordinates are got by negating the coordinates of the original point, so we minus these. Okay, we just put a minus sign in front of these. But now we see that this is indeed a point on the curve, because minus x cubed is the same as minus x all cubed. Okay, so the y value of this point is just got by getting plugging minus x into this here. If we plug minus x in for x cubed, we get minus x all cubed. So this is indeed a point on the curve.